Okay, so yeah, I think I start recording on my side. And yeah, let's start. So hello everyone. Welcome to today's talk. So we'll have Dr. Harideep Nair, a research scientist at Meta, to give us a talk. So Hari is a research scientist at Meta, working on next generation AI accelerator architecture for wearable computing. He graduated from Carnegie Mellon University with a PhD in electrical and computer engineering, advised by Professor Paul Shen and working closely with Professor James Smith. Prior to that, he finished his undergrad studies in the Indian Institute of Technology, Bombay. His research interests are in processor architecture and silicon implementation, targeting energy-efficient acceleration of diverse AI and ML workload. So the mic is yours.
Hey, thank you so much, T, for the warm welcome, and really appreciate the opportunity to present some of my work during my PhD in front of you all. Um, so today, what I'll be talking about is a different type of approach toward computer architecture for intelligent systems. Um, in today's age of LLMs and AI accelerators, um, sometimes it's also important to take a step back and think about um, different types of approaches toward the eventual goal of achieving systems with super intelligence or artificial intelligence. So the work that I'll be presenting today is sort of just like a mere stepping stone toward this, I guess, grand computer architecture challenge of building a silicon neocortex. And our approach is called Cortical Columns Computing Systems, and I'll go over that in different sections today. So here's the outline for today's talk. I'll begin with some introduction and then introduce our research approach that are founded on two foundational works, one from the neuroscience side and one from computer architecture side, and how we leverage both of those to perform the implementation of these new types of computing systems. And then I'll introduce the Cortical Columns Computing Systems and talk about it in three chunks of works. One is beginning with the microarchitecture model, and then the functional building blocks that help optimize the microarchitecture further. And then overall, how do we put all this together into like an end-to-end design tool chain for end users? And then I'll talk about some future works if we have time. There's also a sort of an interesting parallel work that came out of this neuromorphic or brain-inspired approach, but using those ideas for accelerating conventional, traditional GEM. And we have done some collaborative work with Dee on that as well. If time permits, I'll talk about those as well. But majority of the talk today would be about this brain-inspired computer architecture approach. And at any point, feel free to stop me for any questions. So we are all right now going through this huge revolution brought about by LLMs in terms of like AI agents, coding agents, chatbots, etc. And all that's really great, and it has really done a lot of useful things to humans in terms of like improving productivity and applications that have never been seen before, those kinds of things. The interesting aspect is that though these today's LLMs are kind of loosely originally inspired from the brain, they're currently being run mostly on von Neumann Turing computing machines, and that brings a fundamental challenge in terms of the trade-off between the type of compute that it's trying to achieve versus the actual hardware compute fabric that it's run on. So for example, a human brain is really good at sensory processing and pattern recognition, which is the kind of tasks that we are trying to do with AI today, but it's being run on computers or computing systems that were originally built for numeric and symbolic processing tasks. And that's mainly because today's AI compute is mostly matrix, high dimensional matrix multiply, which can be nicely accelerated with GPUs and accelerators along those lines. But the key question here is that for the type of intelligence that we strive to achieve, are those these kinds of von Neumann machines the most effective type of compute fabric, or is there something that we can explore based on how the brain itself performs compute? So if we look at the types of compute, the brain performs vastly different spike-based compute rather than operating on real values and high-dimensional tensor processing, and that kind of naturally also enables brain to perform incremental online learning with very little power compared to the amount of power that we're burning today to perform backpropagation-based training of like billions and billions of parameter models. So there is like huge 3 to 5 orders of magnitude difference in terms of the energy efficiency aspect when we look at the compute fabric. And this chart kind of motivates that, but this is ancient, compared to the times we are living in right now. Nevertheless, it shows an interesting trend. And in some sense, this trend has only gotten worse since these huge models have arrived. Right. What this shows is year on the x-axis and training compute in log scale on the y-axis. And what it essentially shows is that the training compute has been increasing about 10x per year over the last decade or so before 2020. And in comparison, Moore's law that drives hardware is doubling at best every like 24 months. And this is about 7 to 8x slower, compared to the training compute scaling. And this manifests as like about 500x over 3 years, for example. And the way we have been dealing with this issue, and we still are, is by just plugging in more and more GPUs. And today, the largest LLM compute, they're being run on millions of GPUs, which is overwhelming to think about, when we look at that scale, right? So what this motivates is like these two research questions, like this, all of this is great. It definitely is, has contributed a lot of positive accomplishments to the world, but can we, instead of like using these conventional computer systems that are based on a paradigm that dates all the way back to Turing and von Neumann, is there a new computer architecture and implementation paradigm that can better enable the mimicking of human sensing, perception, and cognition in computing machines? So is there such a computer architecture approach that we can look at? And if so, can this be done by reverse architecting the human brain, or neocortex, which is mainly the intelligent part of the brain? Can we reverse architect this by leveraging currently available silicon technology by appending new building blocks and creating design exploration synthesis tools? And there are a lot of, obviously, neuromorphic works out there that are doing research in different domains. For example, there's research being done in ultra-low power analog domain. There's research being done in terms of developing new exotic devices like memristors and so on for performing compute, which are all highly valuable. But to distinguish our approach, the main aspect we are trying to do is trying to come at it from a computer architecture perspective and leveraging currently available silicon technology to kind of show a proof of concept implementation. And obviously in future, there could be a lot of optimizations by all these domain-specific works as well. So our approach is is based on two foundational works, one coming from the neuroscience side and the other one from the computer architecture side. So the interesting aspect today compared to like 30, 40 years back when Carver Mead started his neuromorphic quest is that we have learned a lot more about the brain from neuroscience perspective. And one of the books that was published a few years ago by Jeff Hawkins, who's a famous neuroscientist, claims that the fundamental compute unit in the neocortex is a cylindrical structure, which is called a cortical column, and it houses the universal algorithm to intelligence in the form of abstract structured reference frames. So that's where these terms cortical columns and reference frames come from. And what the neocortex is essentially these cortical columns replicated like 150,000 times. So what it means is from the intelligence perspective, more number of cortical columns in the brain means more intelligence. And this has been kind of observed from like different types of species, all the way ranging from like fruit flies to mice, monkeys, and humans. So that's some interesting concepts from the neuroscience side. From the computer architecture side, can we implement this structure of cortical columns in hardware? And if so, what does that entail? So Jim Smith has done a lot of research for more than a decade on these different types of neural networks called temporal neural networks that are founded on the idea that compute can be performed based on time, and that's where the temporal aspect comes from. And the human brain itself uses time as a resource to perform compute. And we'll see an example of that as we move on. And our idea is to leverage both best of biology and silicon and mesh them to perform efficient hardware implementation of this type of intelligent compute, and demonstrate it using some targeted applications, build a hierarchical processor organization, and demonstrate efficient hardware implementation in direct CMOS. So let me give a brief overview of these two works in terms of what's most relevant to set the context. So coming from the neuroscience side, this new theory of intelligence termed as thousand brains theory, and it's called thousand brains because every cortical column in the neocortex acts like a small brain in itself, and then there are like hundreds of thousands of those. So they all come together to communicate and achieve consensus on tasks, ranging across modalities, like sensory modalities like vision, audio, and so on. But the key idea is that regardless of the modality, every cortical column has some uniformity associated with it, and in terms of how it achieves intelligence. And that the way it achieves intelligence is somehow encoded in this abstract structure called as reference frame. And that's also something that we'll see in the coming slides. So like I mentioned, more number of CCs or cortical columns implies higher intelligence. And a single cortical column in itself is powerful enough to model like complete objects. So if you think about it from a CAD 3D perspective, right, you can have like cortical columns associated with vision, associated with touch. By the way, are you able to see the cursor when I point to stuff? Yes, awesome. So the classic view in traditional neural networks is that you have these layers and layers of neurons, and then you kind of filter out simple features, and then they form complex features, and then you recognize entire objects. There is some sort of hierarchy similar to that in the brain as well, but it's across not just layers, but it's also within a layer. So what it means is that you have like different cortical columns across layers, and each cortical column is not recognizing a simple feature, but in itself is powerful enough to model objects. And it's it's modeled across different scales as you go on, and it's also modeled across modalities. And all these cortical columns talk to each other and achieve consensus. So that's how you're able to like touch some object, and then when you then later look at that object, you kind of recognize, oh, this is the object that I touched, because there's communication across modalities. But the idea is that can we take some of these concepts and implement in hardware? And we'll see that. This is just a slide, again, taken from Hawkins' works. And he's created this company called Numenta, which has published a bunch of neuroscience papers on this topic. But this kind of shows that visually. If you look at a car, for example, the different features like tire or window pane and so on are basically located at certain locations with respect to each other. So a reference frame in this example, in a sense, is modeling this car as a set of features at certain locations. And so this idea of storing features and locations is something we'll come back to when we look at how do we think about implementing this in hardware. So that's from the neuroscience side. So we have this idea of cortical columns and reference frame, which is key to achieving certain intelligent aspects. So from the other side of work that Jim Smith has done, he has proposed this new type of neural networks called temporal neural networks, or TNNs. And this branch here in this taxonomy of neural networks is what TNNs entail. So what are TNNs? TNNs are a special type of neural networks that employ spiking neurons as observed in the brain. They encode information in terms of time, which essentially means the timing of spikes encodes the information, as opposed to other form of encoding, which is rate encoding, where the number of spikes within a certain time window encodes the value. So that's called rate. There's some neuroscience backing to it, mentioning that a lot of like the visual sensing is being done using temporal encoding, where the time of the first spike is encodes the most amount of information. And that's, as we will see, that's also very efficient to implement in hardware. And then learning is done by a very special form of local algorithm called spike timing dependent plasticity, or STDP, as opposed to this global gradient-based backpropagation. And this is what also enables brain to kind of use subnetworks to learn things without having to change every single weight for every new learned aspect. It's able to achieve local learning. Again, something that can be implemented efficiently in hardware. But is the idea behind TNS. So spiking neurons, temporal encoding, and local biologically plausible learning. But the idea of spiking neuron-based neural networks or spiking neural networks is not new. It has been proposed by someone called Mass a long time back, and there's a lot of other works on spiking neural networks out there as well. But unlike other SNNs, there are a few aspects to TNNs that are interesting. Apart from these three tenets, neuromorphic tenets of spiking neurons, temporal coding, and HTTP, there's also this simple compute model, which is we perform integer low bit resolution operation, and we perform simple operations like count, add, and rank. And we'll see some examples of this. And there's no multiply, which is bulk of the hardware complexity in today's accelerators. And that's also something we observe in the brain. Brain does not inherently perform multiplication, but it's more sort of simpler decomposed operations. And the other key aspect is that there's also a structural hierarchy associated with the brain. It's not unlike a lot of works that basically stack together layers of neurons and connect a bunch of neurons. There's an informed hierarchy in the brain, which goes from like neurons to like larger compute units like mini columns and then cortical columns and so on, which is also interesting to keep in mind. So thinking about cortical columns and TNNs, the way we've connected these two approaches is by having this abstract model where you have an agent that is sensing information from the environment, and this information is stored in a structured way inside a reference frame. or macro column as it's just shown here. But in this slide, all we have to keep in mind is like there's an agent that essentially you can think of it as your eye scanning an object, right? It's looking at, okay, I see this feature at this location and so on and so forth. And then that information is stored efficiently in this reference frame. And then later the agent, when it requires someone to make a decision as to what the object is, it can import information from this reference frame. And then there is this loop of continually updating information. So the details, I won't go into the details here, but that's kind of like the high level idea. And I'll point you to the papers for more details. But let's keep this idea of implementing a cortical column as an agent plus reference frame. This is the idea that I was mentioning earlier. When we try to implement a system from a computer architecture perspective, hierarchical layers of abstraction is always helpful. Like how we build computers using adders and decoders, etc., and then build larger units like ALUs and then CPUs and so on. In biology as well, we see some sort of hierarchy. So it's not just a bunch of neurons connected, but it's a bunch of neurons in a specific compute block called a mini column, which a lot of which come together to form a cortical column and so on. And that hierarchy is kind of shown here. But hierarchical abstraction is something fundamental to computer architecture when we build systems. So there's something we'll keep in mind as well. So I'll get into, I'll show details of this as we move on, but this kind of shows some of the concepts that we keep in mind while tackling this problem of implementing, let's say, cortical column. So the way we define a cortical column computing system, or C3S for short, because it's a long name, is that it needs to have a few capabilities. One is that it should be able to perform brain-like compute and brain-like sensory processing, which is energy efficient when implemented using standard CMOS technology, and truly intelligent, and not in the sense like achieving actual intelligence, but just from intelligent in a few simple senses. Like you should be able to learn rapidly with little data, as opposed to having to go through like millions of text inputs or millions of images. You should be able to learn continuously without forgetting the previously learned information, and you should be able to learn with structure. And by structure, I mean the structured hierarchy of compute units, rather than a sea of neurons, for example. And we've broken down this work into three major areas. One is coming up with the baseline microarchitecture model of implementing this. And then we propose some foundational functional building blocks to optimize the hardware further. And then we put all of this together into a design tool that end users can use, that spans all the way from PyTorch layer all the way to post layout netlist. And we'll get into those. So this just shows that microarchitecture model in terms of agent and reference frame. So again, just to keep in mind, agent is just something that gets some sensory features and then makes some decisions. And this can be implemented using temporal neural networks. And there is also more involved reference frame structure, which has some subcomponents to it. But the idea is that through this continuous movement of the sensor and collecting features, it kind of stores a map of what features have you observed for this object at this location. And then that is sort of the information that the agent will use to make decisions. And we see some works on that as well. Yeah, so that's the main idea. Now, now I'll start going into like some of the details of each of these works. Before that, any questions on like the high level ideas presented so far? Okay, so let's keep cortical column and reference frame and temporal neural networks in mind, and let's see what we can achieve with those. So the five major questions that we address here is, by leveraging the convergence of Jim Smith's DNNs and Hawkins' cortical column neuroscience theory, can we implement it using standard off-the-shelf digital CMOS? Then can we further optimize it by building custom macro cells? And then can we implement some of the major bulk of the compute, which occurs in what we call as a synaptic array? Can we implement that in SRAM, which significantly improves the efficiency further compared to implementing it using flip-flops? Then can we implement a reference frame using content addressable memory because it's sort of a map? And then can we make a design tool that lets users perform easy design space exploration and automation spanning PyTorch to layout? So these are the works that we'll touch on. So I'll try to present the major, I guess, the overarching ideas in each of these without going too much into the detail, but there are papers linked for every one of these works that go into more details. And of course, feel free to contact me after the talk as well if you need any more information. So let's start with the microarchitecture implementation baseline work that we've done. So this work essentially is, it kind of proves the feasibility of implementing something like this in digital CMOS. And we have shown some of the efficiency aspects to it as well, and some biologically desired features like online learning with this kind of implementation. So before we implement such a system, the very first thing to think about is, because all of this is based on brain-like compute, which is done on spikes, how do we implement a spike? What does a spike even mean in hardware? So a spike is simply a voltage pulse, and that's it. So there are different ways to encode a spike. You can implement it as a single cycle pulse, or you can implement it as an edge transition, or you can implement it as a multi-cycle pulse. So in our work shown here, we implement a single spike as a multi-cycle white pulse. So each of these rectangles is a single spike, and you can encode information in the timings of these spikes. Essentially, for example, if you're sending an image patch, the pixel intensity values can be converted to spike times, and then you just literally send spikes at those times. So one interesting aspect here is that we don't store the spike times as binary values and then perform like binary compute. It's rather compute happens literally in time. So if the pixel value is encoded as time 7, then we wait for 7 clock cycles and send a spike at that time. So this also enables us to operate in a low resolution mode. Obviously, we cannot have like numbers like 1,000 because then we have to wait for 1,000 cycles to send a spike. So we operate in about like 3 to 4 bits of resolution, which is actually what has been typically observed in the brain as well. And we see that, industry is also going towards lower and lower resolution and coming up with interesting ways to compress data into smaller bit widths. So keeping this in mind, so we have these spikes encoded as these voltage pulses, and the timings of those spikes matter. And we calibrate those times using unit clock cycle. And then there's a concept of a larger clock called gamma clock, which is used to separate out different computational waves. And by computational waves, I just mean like different inputs, like let's say 2 images. So the first image is here, and the second image comes after the gamma clock edge. And so the gamma clock essentially lets you separate out the waves and lets your system reset between different compute waves. And this is also directly inspired from biology because our brain also has these gamma oscillations that perform this kind of reset. So that's one of the foundational aspects. And there's a specific reason as to why we use 8-cycle wide logic pulses for 3-bit weights. It is essentially to optimize hardware significantly. What we achieve with this is that the same, because the compute is time-based, we need some sort of counters in hardware, which are implemented using flip-flops. So what we do is we literally store the weights in those counters and make sure that the weights don't get destroyed during the counter's compute, because when the counter is counting, you're essentially changing the weights. But we make sure that it's always restored. And what that enables us to do is we can eliminate a separate storage for weights. So we essentially store weights within the same counters that performs the compute. And that's an interesting optimization we were able to do by calibrating the pulses in a specific way. But if you look at the neuron building block that we want to implement, this is kind of like the adder in the sense that in sense of foundational compute unit, right? So this is like what is the base compute, and what it essentially does is you have this whole thing is a single neuron, and a single neuron has multiple inputs where you can get multiple spikes, and these spikes go through a weight. We call these synapses because these are connections to different neurons. So what happens is based on the weight of each of these connections, the spikes get modulated into response functions, and these response functions get accumulated into the neuron body. This is where the adder type of compute happens. But notice that the input is coming as just a single voltage pulse rather than multi-bit parallel value. And then when this accumulated body potential crosses a certain threshold, it fires an output spike. And this is foundational to any spiking neural network work that you'll see, which is, integrate and fire. One aspect that we don't do is leak. There's a lot of other models out there that perform leaky, integrate, and fire. What it means is the body potential kind of leaks over time, which is what is observed in biology. But what we kind of ask is that because of biological, it's an artifact of just being biology, because we don't necessarily need to implement leak if it doesn't contribute to compute. We can always reset it in hardware synchronously, so we don't need to leak to reset. So we just kind of ignore the leak for making the compute simpler while having this kind of ramp to keep the main part of the compute. But nevertheless, let's say in simple terms, we get spikes. It generates these response functions that get accumulated, and then the neuron fires an output spike when it crosses a threshold. So we need to implement all of these aspects. So we need to implement a synapse, which literally stores the weights. And the weight is what determines how strongly this input gets correlated into the body potential. We also need to implement the response function logic, because how does the synapse turn this spike into a response function? So that's what is called as a readout logic, because we read the spike out into a response function. And then we also need to implement STDP learning, which is the logic that will update the weights based on what we observe the output spike and the input spike. And in simple terms, the learning is so simple that what you look at is the timings of the output and input spikes. So if the output spike occurred after the input spike in time, that means this spike has contributed to this output, so you increase the weight. If it's otherwise, you decrease the weight. And there's somewhat nuance to it, but in simple terms, this is what the learning entails. So we need to implement synapse and STDP. And obviously the neuron body, which is the part that accumulates all these responses and then uses a threshold comparison to fire an output spike. And then this output spike will go to downstream neurons and so on. So just keep in mind that so far we are talking about just a single neuron, because we'll then use this to create larger compute units like mini column and then cortical column and so on. And the basic idea is that we implement once we implement a neuron, we take multiple of those and add what we call as an inhibition block to it to form this larger compute unit called a mini column. This is sort of like an ALU when we think about it. And the idea is that mini column itself is able to perform effective pattern recognition. Like it can cluster inputs into different patterns, as we have seen in our work. I'll show some results as well, but simply put, what it does is you have this synaptic array, which is essentially the cross connections across the inputs and the neurons, and every one of these connections has a weight. But the idea is that after the neurons fire their output spikes, we use inhibition to filter out the outputs. We say that we only care about the neuron within this mini column that fired earliest. Let's say at spike time 2. That's the earliest time. Infinity here means no spike. And we say that neuron is the winner. So if you want to perform if you want to recognize certain patterns or cluster them, we say that, okay, this input that we've seen falls into cluster number 4 or 3. because it's like the third neuron, 0, 1, 2, 3, right? And so on. But this mini column itself has a specific, function associated with it. And this also is inspired from biology because we see those structural hierarchy in biology. And so the way we implement this is that, so as we see in the mini column, we have the synaptic array, this array, and then we have the neurons that accumulate the responses, and then we have the inhibition. So the synaptic array is where the majority of the compute happens because you generate response function, you store the weights and so on. And like I was mentioning earlier, we implement the synaptic array using a counter, and we literally store the weights in this counter as well. And this just kind of shows like what we do is when an input spike comes in, the counter gets kicked off, and then it starts down counting. So the initial value is the weight value that it's at, which is 5 in this example. So it starts down counting, and we output a response. And then as we see, like the response keeps increasing until the counter hits 0, and then we saturate. So after that, no more output. So this essentially is a specific type of response function. So what this counter has done is when it gets a spike, it generates something like this red curve. And these red curves are what get accumulated into the neuron body. And what we see is that we always enable the counter such that it counts it back to the original value. So like it started at 5 and it will end at 5. So that way we don't destroy the weight during inference. And the weight is only like updated by STDP. But the overall idea to take away from here is that we implement synaptic array using counters, which lets us eliminate a separate weight storage because we literally store the weights inside the counters. And that optimizes the microarchitecture here. And then using that, this just shows the hardware implementation of these different blocks. All the details are present in respective papers, but it's relatively simple because of the simpler compute logic. So as we see, the learning itself can be implemented using some gates and latches and so on, and so forth. So using this implementation, what we've done is we've tried performing time series clustering with it, and we see pretty promising performance. Like when we compare it with highly complex recurrent neural networks and so on, for this, we still find competitive performance while being extremely power efficient. Our models for this pretty much consumes under 40 microwatts power in 7 nanometer CMOS based on this microarchitecture model. This was one of the ICAS paper. And then we've also demonstrated how we can make larger temporal neural networks by stacking these layers. But within each layer, we have this hierarchy of mini columns with inhibition and then neurons. And this is what we call as a feed-forward temporal neural network, which we'll see we can later use to build agents and so on in the cortical column. We'll see a separate work that we did focusing on the reference frame part. But this just shows kind of like the network architecture that you are mostly aware of, right, in terms of different layers and so on. But yeah, the idea is that you can stack together multiple layers as well if needed. And we have done MNIST with it. Just as an example, we've overlaid our data on like a chart that we got from this book. But comparing it to different devices that perform MNIST, we see, so x-axis is error, y-axis is power. This is the area we want to be in because this is low power and low error. And these blue dots are like different DNN implementations, like small, medium, large, and we see they're in the favorable area, like power efficient, with 99% accuracy for this 4-layer DNN on MNIST. Now, given our baseline microarchitecture that's implemented using counters and adders and so on, can we optimize it further? So that's where we looked at different functional building blocks. So for this work, what we've done is we've looked at the key functionalities that we want to implement, which is like, let's say, count, rank, and so on, because ranking was involved in inhibition, where you rank the timing outputs and you determine the earliest spiking neuron as the winner. So those kinds of compute. So we want to perform those compute. So since we know our compute really well, we can actually hand design custom macros that can efficiently implement those with minimal transistors and gates possible. So that's what we did, because earlier we implemented it in Verilog, and then we just used standard cell library and synthesized it and got the numbers. But what we did here is, can we do better by making our own standard cells, custom cell macros, by hand designing the compute blocks. So we identified 9 areas of functionality that we can make hard macros out of. 5 of those macros are for synapses, 1 for inhibition, and 3 for utility functions. And this just shows like the actual macro implementations. I've linked the paper in the previous slide. Sorry, that proposes this. But yeah, these are just the macros, the 9 macros, literally their depictions. But what we have showed is, so if you look at the earlier benchmark of time series clustering, it actually consists of 36 sub-benchmarks across different modalities of time series, like ECG, like motor, like different kinds of like radar sensors and so on. What we observed is when we use our own custom cells, obviously that increases the netlist generation speed a lot. It's at 4x faster because the tool doesn't have to put together standard cells from during the synthesis stage. It has already delivered macros. But other than synthesis time, we see significant PPA improvements as well, about double digits in like power area and energy delay product when we implement using these macro cells. And this library is something we call as TNN7 because it's a 7 nanometer cell library that was built on top of open source ASAP7 library and specific to TNNs. So our largest TNN column with on-chip learning using HTTP consumes about 40 microwatts power and 0.05 millimeters square, while performing competitively to other networks on time series clustering. So that demonstrates the power of like building custom macros. And this is that previous MNIST example, but now repurposed it with the custom macros. So the red stars were the original data points from our microarchitecture. Now, if we use custom macros, it gets slightly better. And this is actually log scale, so this is a decent improvement. And about double-digit improvement in terms of percentages, right? So it gets us closer to this lower left part if you use standard custom macro cells. So that kind of demonstrates this. The next aspect I want to touch on is we have optimized it using macro cells, but what we're still doing is using flip-flops, inside those counters to store weights. Now there's a huge optimization potential if you move all of this to SRAM. So not just store the weights in SRAM, but move the compute also to SRAM. So this is the work we explored in that direction, compute in memory, by performing this TNN compute literally inside SRAM. And the idea is each of these points here is, instead of using the counter-based FSM, we want to implement it in like a memory cell. So the details of this are in the papers, but the key idea is that we store a bit in this modified SRAM cell, which has, so we added tri-state buffer and some switches in here. And the idea is that we want to implement counting within this set of SRAM cells. And the prior works that we have seen in this domain usually implement counting as a multi-cycle process. Like they use multi-cycle shift to perform count, but we want to perform counting in single cycle. So because our implementation is based on time. So how do we perform that in single cycle? We perform this rippled counting effect. So for example, if you want to down count by 1, all we do is we flip all these zeros to ones from right to left until we reach the first one, which gets flipped to 0, and then no more flipping after that. So this flipping is essentially a down count. And this is what we have implemented in this SRAM cell by using this tri-state buffer and switches, which is carefully designed such that it enables this rippled counting, and then it stops the count based on the states across these SRAM cells. So hopefully the overall idea makes sense. And once we figure out how to implement this rippled counting inside SRAM cell, the other aspects to think about is how do we implement the readout part of it? So you have the counter. Now, how do you implement the output generation from the counter so that you get this response that we saw earlier? So that is implemented using this logic, which essentially puts transistors together to implement the digital logic that we want. And same with the learning as well. So we have different cases inside the learning depending on the input and output spike time. And again, those digital logic functions are implemented directly in transistors in here using CMOS logic design, fundamental principles. And we put all of this together into like a counter plus response function plus STDP module. And all of this is kind of packaged as an SRAM synapse cell. So using this idea, we compared it with the previous implementation, and we've seen this has potential for 40% improvement in area, and 20% in power, and then 24% in energy based on the power delay product. And this is implemented only for 3-bit weights. And that's typically the range we operate in, 3 to 4-bit weights based on the resolutions observed in the brain. But this work mainly, what the idea is to prove the feasibility of implementing something like this within SRAM and reap the benefits of SRAM based memory rather than flip-flop based cells. Again, we've demonstrated this also on the ECG work and other time series work, because that's a small enough model to characterize and implement. So far what we focused on is like the synaptic array, which literally performs like majority of the compute because it generates the response functions and so on. And we can build temporal neural networks based on that, which can feed into the agent part of the cortical column from the big picture perspective. Now, from the reference frame side of it, which stores a map of features, locations, and so on, how do we implement that? So that's where this next building block work we did comes into play. Because we think about this as a map, which is sort of like you want to send a query to it and get, okay, what's the feature that I see at this location? It's sort of like a key value thing. So that can be implemented using CAMs. That's the connection we made. So this work performs that implementation. And this just shows what we're supposed to achieve with this in sort of like an application perspective. So let's say you have 3 objects and they have essentially the same 3 features, the triangle, star, and circle, but they are distinguished by the positions of these features. So we store these features and locations and the class of the object in here. And as the agent moves through the environment, what it does is, let's say if it first encounters this triangle at 1,3, it searches this reference frame and sees that it's present in all 3 objects. So far it doesn't know which object it is. It says it could be 1, 2, or 3. Then it sees a circle at 2, 1, and it sees that, oh, it's only now possible from objects 1 or 2, not 3. So it's sort of like temporally narrowing down, filtering and enriching information over time while keeping the previous inferences in mind. And then if you see the star at 3, 3, it knows for sure the object is 2 and not 1 or 3. So it has to like sequentially infer information and collect information while doing this like query in the CAM. So it's not like you do a query and then forget about it, but you have to store the information from it and then do that. So this is implemented as sort of the state machine, and we have some micro ops and macro ops in it. But the main idea is that you can look up data, you can store, delete, and so on. And I won't go into detail of this, it's there in the paper, but the overall idea is that you can perform this CAM-based lookup using this sort of state machine that sequentially infers information. And we have, again, tried to synthesize it in ASAP 7. And we've seen that you can implement like a 1024 entry CAM. This is something we call as NERD CAM because it stands for neuromorphic reverse ternary CAM. And reverse ternary because we enable it to query using don't care bits. That's where the ternary aspect comes from. because what it stores is essentially like a long bit array, which has some parts dedicated to feature, some parts dedicated to location. So if we want to predict a location based on feature, we provide the feature bits and then say the location bits are don't care. And then it does the matching based on that. So that's the idea of ternary. And reverse ternary, because we do present don't care bits in the input rather than inside the memory. So there are traditional works on ternary cams, but the ternary there means that they store don't care bits. They don't query with don't care bits. Since we are doing the reverse of it, we don't store don't care bits, but we query using don't care bits. We say it is reverse ternary cam. But the main idea is that we implement like the key sort of inference and map storing mechanism of reference frame using this cam structure that basically stores features and locations and the class, a triplet set of information. And we have looked at Numenta's work on MNIST, where they try to use their kind of reference frame approach towards it. So we try to implement their application in using our NerdCam implementation, which is sort of the specific bits, like 128 bits for feature, 25 for location, and 10 bits for class, because 10 digits. We've seen that we can pretty much do that with, in this case, 1024 size NerdCam in 400 milliwatts power in 7 nanometer, and with an area that is about 0.1% of typical mobile SoCs. So the idea is that once we mature this like reference frame based approach enough to have like processing units based on that, this work proves that or shows that with a fraction of the area cost of a traditional mobile SoC that has like CPUs, GPUs, NPUs, a dedicated processing unit based on like a reference frame can be implemented using a fraction of that area and can perform some intelligent, biologically plausible type of compute. So in this case, the MNIST compute we do is not the traditional like present an image, detect what image it is. Instead, we present patches of image in a sequential fashion, sort of as how your eye would scan an image. And then you can also do it in a random way. Like you can look at top left first, then the center, then the top right, and so on. And what we see, that's where the robustness comes from. So we see that that kind of functionality can be implemented using this NerdCam in efficient area and power. So that's kind of like the feasibility concept that we've presented using this work. Yeah, like I said, like there are some works that compare this with other approaches, and in this kind of like biological scenario where you're not presenting an image but looking at just a small patch of it and in a sequential or a random manner, it gets like 80% compared to like other LSTM approaches, about 65%. And we see that NerdCam with even 500 entries can do this while outperforming these baseline works that Numenta had compared against. So that's kind of like this work. So we looked at the microarchitecture, we looked at the custom macros to optimize it, we looked at the compute in memory aspect of it, and then we looked at a CAM-based implementation for reference frame. Now, putting all of this together, what we've done is propose a toolchain called DNN in 2024, and we're working on, our group is working on a new version of it called New DNN based on latest neuroscience insights since then. But the idea is that we have this structured hierarchy, like in traditional computer architecture, and we implement all of that into this toolchain. And we have a simulator aspect of it, which has this PyTorch-based functional simulator, which is what we have used to get all the MNIST time series data, like the application data, like accuracy and clustering performance and so on. And then we have the hardware generator aspect of it, which is linked by this toolchain called PyVerilog. So we implement our microarchitecture in PyVerilog, and what this tool does is when you press enter, it does the PyTorch simulation, gets accuracy, etc., and then goes through this PyVerilog to automatically generate Verilog. So it generates Verilog. All you have to do is provide it parameters: how many layers, how many neurons, how many mini columns, and so on, and what's the threshold, what's the HTTP parameter, and so on. And then it'll generate Verilog, and then go through synthesis and place and route, and then provide a post layout netlist out of it. So this toolchain is what we currently call as New DNN, which is under works. But a prior version of it called DNN has been published in TCAS journal. And some interesting aspects of it is that we can do online learning using the biological HTTP learning. This just shows kind of like we only train it based on 9 digits instead of 8. So like instead of 10. So we hit the digit 9 during training. And then during like testing, we just provided the digit 9 and then it picks up on it by itself without forgetting the previous digits. That sort of shows if new information is presented to it, it's able to dynamically pick it up. That's the online learning aspect of it. And then we have generated PPA for time series clustering, MNIST, and reference frame part using this tool chain. And yeah, that's just sort of like proof of concept. Yeah, so that's kind of like I know it's a lot of content, but I kind of wanted to show the overarching picture of the different aspects. I have papers as linked in like all of these different sections, which can go through and sort of like to present this in an overarching research aspect. Here is like the feed forward typical neural networks. Here is like all brain-like functions. And what we like the CNNs are all like this feed-forward aspect. With C3S, we are trying to also look at like this other types of reference frame-based functions, map it to spike time processing, and then eventually build brain-like sensory processors in parallel to like the typical AI accelerators that you have seen on the left side. The other work we have done, also like in collaboration with D, is a bridge between these two works. So like, can we take insights from this part of the research into the traditional AI accelerator part? That's where we kind of use unary encoding to make efficient GEM implementations. And so on. I'm sure D can also talk more about it, but that's just to throw off the another idea we've worked on. So yeah, with that, I think that's most of what I wanted to go over today. But yeah, please feel free to let me know if any questions or reach out to me. I can point you to papers and so on. Yeah, thank you. Yeah, sorry, D, I think I went over a lot of things pretty quick. I don't know if that was.
Yeah, that's very interesting. Thank you. And I think it's a very comprehensive presentation about your PhD work. Very impressive. Yeah, and yeah, any questions from the audience? I think we have let's see, receive a message here. Oh, sorry. I can't see that.
We love MNIST. I think that's the message.
Okay. Yeah.
Who doesn't?
Okay. Yeah,
Yeah.
so any questions from the audience? If any questions, you can just open your mic and speak up. Otherwise, you can, type in the chat. Okay. Yeah, I do have a question, one of the question I have when I do the unary computing research is, I mean, or more broadly, neuromorphic computing research is that compared with the conventional AI, I think its power comes from the fact that it can be scaled up, right? And also in the era of computer vision, before we enter in the large language model, spiking neural networks, learning from the deep learning seems to have a pretty good chance of catching up with accuracy. But suddenly when we enter the large language model era, things seems to, the gap seems to be widened because the model size seems to stay at hundreds of million level versus the language models going to, I don't know, even trillions of models, right?
Yeah.
So what's your opinion in terms of scaling up the TNNs to the level of maybe, comparable to human?
That's a great question. So um, this is something that we think about in terms of like how much of that scale of LLM is due to the artifact that it's based on a fundamentally different type of compute. Like, for example, what it's trying to underneath the hood is trying to do is like learn statistical correlations between all the different numbers and vectors that it's seeing, which takes up a lot and lot of compute. Which leads to like, just put more parameters, just add another zero to the number of parameters and it will magically work well. And that's something that we have seen, right? Trillions of parameters, like you mentioned. Versus in the human brain, we do have billions of like neurons, I think about, I don't remember the number, but there's billions or close to trillions of synapses. but not all of those synapses are doing like one thing. And there's also the other aspects. There's a lot of redundancy in the brain. So that's where, like, if a subsystem, um, for some reason, like, any disease or anything comes, the brain is good at adapting the other parts of the system to like learn, to do how the other part works. So people have seen like those kinds of um,
Sorry, is it my problem? Hi, Harry. I don't know, is it my problem or some?
that is something that requires extensive research on learning itself, because what we have seen with like HTTP type of learning is that it has not been proven to be as scalable as backprop across like deep sets of layers, right? Because that's also not something that the brain does. Brain doesn't have hundreds of layers. It actually has 6 layers of the neocortex stack, and within that it performs local learning. So one big challenge that will come is how do we scale the learning to that level, if you wanted to scale it to that level. But the other side of the question is that really the way to go? That is something that's not clear. Maybe there is a different way of scaling. Instead of having a trillion parameter network, you can have like a million parameter or 100,000 parameter network, like a cortical column based thing, for example, and then have that replicated in parallel, like maybe 100,000 times, right? So these are all multiple small networks working together. And then the main question comes there is like, how do these subnetworks communicate with each other? What's the voting consensus reaching mechanism? And I think that might involve a lot of knock research on hardware, right? And in terms of protocols, what are the efficient protocols that these subnetworks can talk with? So I think like when the question of scaling comes up, the two main aspects to think about is one is the learning part on the first approach, or like the communication part on the second approach.
Mhm. Right.
Um, but yeah, the huge models that we're seeing today is it's kind of unbelievably overwhelming in terms of like the amount of power it takes, right? A small country, for example, so compared to how the brain does. So yeah, the way to scale up is interesting. Like, do we scale across the 10 stacks, or do we scale in terms of parallel compute units, where each is kind of like a simpler version? We
Mhm.
just got like we seen like GPUs, but this is kind of like not a matrix multiply based compute, right? But yeah, I don't know if that answered the question, but I
Yeah,
guess
yeah,
that's the
yeah. So I think these are definitely very open discussions, towards the true intelligence. And also, especially given the hardware we're trying to build, it's very hard to convince the industry to abandon what has been there for decades, right? I mean,
yeah,
it's not decades, it's already kind of a half a century. So
yeah,
starting something new is very challenging, and this is definitely a very bold journey. Yeah,
definitely.
even and also I feel like even and yeah, maybe that's a second question. Even if you want to target CMOS, but there's a way broader community trying to use the analog computing targeting the neuromorphic, right? So there is a very fundamental shift, I mean, or fundamental difference in people's view of how we should approach the human level intelligence and efficiency. If with the analog, a lot of the benefits comes from the analog devices. They are inherently low power, but going
Right,
from CMOS is not as efficient as the analog, but it's way
right,
more controllable. So
right.
the balance here, so could you share any, your thoughts about the balance here or the trade-off here?
Yeah, exactly. That's like you mentioned, that's exactly the trade-off that we've been thinking about too. Analog definitely offers a lot of promise in terms of ultra low power um, processing. Like, we probably won't get to brain-like efficiency with digital, for example. But what we could get to is a stepping stone where it's definitely significantly orders of magnitude maybe more efficient than, let's say, the GPU-based tensor dimensional compute. At the same time, like, one aspect to think about is like when we are looking at something that's very different from what's being done, uh, one way to, I guess, in order to get it adopted, there needs to be a bridge, right, between the current um, current way of doing things and the new way of doing things. So that bridge is what we have thought of as like using the current digital CMOS, because it's something that's we have like trillion-dollar fabs that work based on this, right? So if you have like uh, uh, we can kind of break it down into one sort of like building a computer architecture approach from like algorithmic research, and then proving that using digital CMOS, which is one part of the stack. So that shows that, okay, there's this different type of compute that can offer efficiency because of its like local learning and event-based compute and so on, and get us like halfway there in terms of achieving brain-like efficiency. And then you can take this further, using like potentially analog or other types of devices to bring it down to ultra low power. And then there are obviously challenges there in terms of like how would we migrate from the digital to like the analog, and there's no noise concerns and so on. So I think that's where that part of the research is highly valuable. But I kind of see it as this two-step process where initially to get it maybe like for mass market immediate adoption, you keep the digital aspect and try to tackle the architecture side of things. At the same time, have like highly valuable research on analog that people are doing, and then connect it kind of to get the full uh, transition, right?
Yeah.
Uh, that's yeah.
Yeah, I agree with the point. I agree with the point. You should probably, create two hierarchies and build the proper like abstractions between the two hierarchies. I mean, between the two domains, basically. Then the question is, where is the boundary of that
Yeah.
abstraction, right? It's
Yeah.
yeah, it's very like the I mean traditional computer architecture. You implement you can have all the different microarchitecture implementation, but your instruction set stays the same across different paradigms across the processors.
Yeah.
Yeah. Okay. Yeah. Thank you so much for sharing your research and sharing your thoughts on where we should go in building future systems, maybe the large scale intelligent systems, and also all these kind of very fundamental frameworks to support the C3S systems. And yeah, so I guess that's probably we're sort of running out of time. So that I think that's the end of the today's talk. So let's thank the speaker one more time. And
Thank you. Thank you, Dee,
yeah,
and thanks
yeah,
everyone.
yeah. Yeah, and I will catch up with you later once I arrive at the Bay Area. Okay.
Sounds good. Looking
Okay.
forward to seeing you.
Okay. Thank you, everyone. So I will see you next time.
Bye.
Bye.
Bye.